So far, we have learned about control charts for variables. We learned about X bar chart and R chart. Variables are those characteristics of data that are measurable, such as length, width, height, etc. Attributes, on the other hand, they are not measurable. They are countable. So they can be 0, 1, 2, 3, etc., etc. For attributes, we have two control charts. We have P charts and we have C charts. P charts are used to, for example, monitor the proportion of defective products or defective items in process. And C charts are used to monitor the number of defects per unit. Let's just start with P chart. P charts are used for the observation or the scenarios in which you can place the data in two categories based on a characteristic. For example, good product, bad product, good service, bad service, pass or say or fail. For example, for a process, operate or operatable and don't operate. Or when the data consists of multiple samples of several observations each. For these scenarios and see these types of observation, we can use P chart. Similar to control charts for variables, the control charts for attribute also has a lower bound and upper bound. This is the formula to compute the control charts for attributes, the P chart. This is the standard deviation of proportion P. So that's the square root of P multiplied by 1 minus P divided by N. N is the number of observation in the sample and P is the proportion. Then when we compute the standard deviation of proportion here, the upper control limit is the proportion plus Z multiplied by sigma of P, and the lower control limit is the proportion minus Z multiplied by a standard deviation of P, which is sigma of B. So let's go ahead and do an example, see an example to understand this better and see how this works in practice. If P, the proportion, is not known, which is usually the practice, the reality, then it can be estimated. We can estimate P bar, which is an estimation of proportion P, using the following formula. So P bar, which is the proportion for P, that's the total number of defective divided by the total number of observations. And also we can estimate the standard deviation of proportion using this formula, which is just the replacement of P by P bar. So that's the square root of P bar, the estimated proportion, multiplied by 1 minus P bar divided by N. And the formula for the upper limit control and lower limit control stays the same, except that we're going to replace P by P bar and sigma of P by sigma hat of P. This is called sigma hat, which is an estimation of the standard deviation proportion when you don't know the proportion. So because the formula is an approximation, we approximate the proportion here. Sometimes it can happen that the computed lower control limit becomes negative. So if this becomes negative, you just have to round it up to 0, because the proportion cannot be negative. It can be at least 0. So if you get a negative proportion, negative control limit, lower limit, you just have to round it up to 0. This is the standard normal distribution table from statistics that you can use to either find a probability given the value of Z, or if you have the probability, you can find Z. However, this might be a little bit different from the table that you have seen before. So Z distribution is just a normal distribution. So Z is a normal distribution with an average of 0 and a standard deviation of 1. And if you want to find the probability, for example, the probability that z is less than a value, z star. Z star is a value, for example, 2.8. So you can use actually this table to do that. But you should know that this table is a little bit different, and the difference is that it doesn't count in the probability of 0 and less than 0. So it's only for 0 and beyond into a positive perspective. So what you need to do here is to consider that part that is not considered here. If you remember from a statistic, the probability that z is less than or equal to 0, that's actually equal to 0.5. That's half of this. So that probability would be the shaded area on this curve on the very left. So that would be 0.5. But in this table, it starts from 0 and beyond that in the positive direction. So this means that it does not count the red shaded area. You can actually add it yourself to that. So the probability of z0 is 0 instead of being 0.5. So this means that if the table that you have learned from statistics, the difference between this table and that table is that you have to add 0.5 to these numbers to be equal to the table that you have seen probably. So that would be 0.5 here. This would be 0.504. This would be, for example, 0.7324, another random number here. That would be 0.9925, and so on, so and so forth. So that's the main difference between this table and the table that you have seen here. And this is how you can actually use it to find the probability. So if you know the probability and you want to find the corresponding z value, you need to add 0.5 to that probability if it's actually on the right side. If the z value is on the right side, so the probability must be greater than 50% to find z for that. Or if you know z, then you can find the probability, and when you find the probability from this table, for example this, you're going to add 0.5 to it to count in the left part here, probability of z less than 0. This is 0.5. You need to add 0.5 to that probability you find from this table to include the left part of this curve here. Let's see the example. An inspector counted the number of defective monthly billing statements of a telephone company in each of 20 samples. So we have 20 samples of data, as you can see from the table here. Using the following information in the table, construct a control chart that will describe 99.87% of the chance variation in the process when the process is in control. Each sample in this data contains 100 statements. So we have the statements, the samples, and the number of statements. So for example, for sample 1, we have 100 of a statement, and out of those 100, 7 are defective. That means 93 are correct. Sample 2, for example, has 10 defective statements. That means that 100 minus 10, which is 90, are correct. When I use a random one, for example, the sample 8 has 18 defective statements, so that means 100 minus 18, that's 82 correct statements. And another, for example, sample 20, it has 21 number of defective statements, so that means 79% of it is correct. So we have this data here, and you have the formula down here. Since we don't have the percentage, we have to estimate it using the formula here. So try to solve this problem using the formula here and the information given. What you need to know as a tip here, Z is not given here, so you need to use a Z distribution, a normal distribution table, or Excel, and based on your knowledge that remember from a statistics course to compute the value of Z here, to find the value of Z here. When you are done, you can come back to see the solution, how we can solve this problem. So let's solve this problem. Before we move on, if you look at the formula here, we need to compute P bar, or the average or the estimation of P, because we don't have it, and also the standard deviation sigma hat, and also we don't have Z, we need to find Z. So let's first go ahead and find Z from the table. This is table A, we can find Z from this. So the problem says that the probability that's given in the problem is 99.87. 99.87, as we said in the when we described this table, you need to add 0.5 to the numbers here to look at it, to these numbers to be able to find the corresponding Z value. So 0.99.87. So this means that if these values in the table doesn't have this 0.5, so you subtract 0.5 from this and you get 0.4987. Then you look for 0.4987 in the table. So let's look for it. It's going to be here. And that corresponds to Z equal to 3. So Z is 3. So now we know Z. Z is 3. Let's go ahead with the rest of the formula. Next, we compute the estimation for the proportion, or P bar. So P bar is going to be the total number of defectives in all of the samples that we have divided by total number of observations. How many defectives do we have? What you need to do is you need to sum up all these defectives from all 20 samples that we have, and that's actually equal to 220. So that's 220 here, divided by the total number of observations. Total number of observations, we have 20 samples. Each sample has 100 statements, so that's 220 multiplied by 100. So that's 220 divided by 20 multiplied by 100, and that's going to be equal to 0.11. So P hat is equal to 0.11. Now that we computed P bar, we can compute the standard deviations. Sigma hat would be the square root of P bar that we computed here, multiplied by 1 minus P bar divided by N. N is the number of data in each sample, which is 100. So that's 0.11 multiplied by 1 minus 0.11 divided by 100, which is 0.0313. So that's sigma hat for proportion. Now, if you plug in all these information that we have in these two formulas, you're going to get the upper limit and lower limit for the control chart, P control chart. So that would be P bar, which is 0.11 here, 0.11, plus Z, this is Z, we find Z equal to 3 from the table, multiplied by sigma hat, which is 0.03, find it here, 0.0313. So that would be, gives us the upper limit for the control chart, that's 0.2039. And if you use the other formula, this formula, you're gonna get the lower limit. So this is the lower limit and upper limit. If in any example that you use the estimation P hat to compute these values, again, just as a reminder, and you get a negative, for example, number here, you have to round it up to 0. So this wasn't the case here, but just for the record, remember to do that. All right, so now we have the upper limit and the lower control limit for the proportion of defective items. We want to now use this control chart to actually test whether uh, the the process, this process, is in control or not. So what you need to do is you need to find a proportion for each sample. So for example, we know that the first sample, the second sample, the third, fourth, up to the 20th sample. So for each sample, you find the percentage of defective items. So for example, each sample, you know that it has 200 actually statements. So this makes it easy to compute the defective percentages. So for this one would be 7%. So that's 0.07. For the second, that's 0.10. For the third, that's 0.12, and so on and so forth. So when you compute those, you have to check whether these values would actually fall within the acceptance range here. So all values must be between 0.0161, the lower limit, and 0.2039, the upper limit. And actually, if you just look at here for the sample 20, the p hat, the proportion here would be 21%. And 21% is not within this range. So this means that the process is not in control. Here's a visual demonstration or illustration of the control chart. So on the x-axis, we have the sample number from 0, 1, 2, 3, 4 up to 20 sample that we have here. On the y-axis, we have the fraction of defective or the proportion of defective, and that's from 0 to 24%. It doesn't have to be 24%. It's just what matters here is the lower limit and upper limit. So the lower limit is 0.0161 and the upper limit is 0.2039. And if we find and plot the percentages for each of these defective for the 20 samples, if you plot them here, it's going to be these. So as you see here, these are all the plots for the proportion of defective items here. And this is the line for the upper control limit. This is the line for the lower control limit. And as you notice here, this one, which is for the 20th sample that we have, 21%, is outside of this control chart limit. So this means that this process is not in control according to the data that we have. The process is not in control. The other control chart for attributes is the C chart. C chart is used for those data and in those scenarios that you can count the number of occurrences of something per unit, but you cannot count the number of non-occurrences of that. So this is in opposed to the P chart scenario in which you could actually put the items in two categories and you could count the two categories. For example, you could actually categorize products based on whether they are defective or not, and you could count the two categories, the number of defective and the number of non-defective. But for C charts, you could actually categorize items in two categories, but you cannot count both of them. For example, the number of scratches, the number of chips, dents, or error per item, you can count that category. But the other category, which is the number of non-scratches, the number of no chips, so that doesn't make sense. But you cannot count the number of non-scratches or non-chips or non-dents. Or for example, you can count the number of cracks or faults per unit of distance, but you cannot count the number of non-cracks. You can count the number of breaks or tears per unit of area, but you cannot count the number of non-breaks. You can count the number of bacteria or pollutants per unit of volume, but you cannot count the number of no-bacteria. So, or you can count the number of calls you receive, the number of complaints, one unit would receive the number of failure per unit, but you cannot count the other category, which is the number of no calls. How many no calls you received, right? It doesn't even make sense. The number of non-complaints, how many non-complaints did you receive? So you cannot really count the other category. So for these characteristics and for these types of data, we use a C chart and not a P chart. You see here the formula for the control chart for C chart. C here is the average, C is the mean, and the square root of C is the standard deviation. So the general formula stays the same for the control charts, is the average plus minus Z multiplied by the standard deviation. Here, the average is C and the standard deviation is square root of C. What if you didn't have the average C? If you didn't have it, you have to estimate it based on the sample, C bar. And this is the formula to use to compute the estimated average. That's the number of defects divided by the number of samples. So let's see an example to see how this would apply in reality. Rolls of coiled wire are monitored using a C chart. 18 rows have been examined, and the number of defects per roll has been recorded in the following table. Is the process in control or not? Plot the values on a control chart using the 3 standard deviation control limits. So these 3 standard deviation control limits, that means that if you remember the formula for a control chart, that's the average plus minus Z multiplied by standard deviation. So Z multiplied by standard deviation multiplied by. So here it says 3 standard deviation. That means that Z is actually 3. So please now pause, try to work on this problem, try to solve this problem, compute the control chart, the lower limit for the control chart, the upper limit for control chart, and then try to see whether the actually rows of coils wire this process is actually in control or not. You can also plot it. After you tried your best, come back to see how we can actually solve this and how is it solved. Let's see how we can solve this problem. First of all, this is a C chart problem because we can count the number of defects per roll of wire, but we cannot count the number of non-defect per wire. So per roll of wire. So this is a C chart. For the C chart to use, because we don't have the average number of defects, so we have to use the estimation of that based on the sample that we have. The formula for that is C bar is equal to the number of defects per all the samples that we have divided by the total number of samples. So we have 18 roll of wires. So 18 is in the denominator, and in the numerator is the number of defects. So what we need to do is we need to add all of these defects that we have for all of the samples, and that's actually 45. So that would be 45 divided by 18, and that's 2.5. So the average defect per unit is 2.5 here. And then we're gonna use these two formula to find the upper and lower control limit for this chart. C bar is 2.5 computed. For the upper limit, we're going to use the plus. For lower limit, we're going to use the minus. Z here is 3 based on the problem statement. So Z is 3. And the standard deviation or a square root of C is a square root of 2.5 because C is 2.5. So if you do that, you're going to get 7.24 for the upper control limit, and you're going to get negative 2.24 for the lower limit. And so this is the case and scenario that you have to round this up to 0 because it doesn't make sense to have negative number of defects per unit. So the lower limit would be 0 and the upper limit would be 7.24. We can now plot this control chart on a chart here. As you see, the lower limit is 0. We round it up to 0. So this would be exactly the x-axis here, and the x-axis is the sample number, and sample 1, 2, 3 up to the latest, the last sample, which is 18. And on the y-axis, we have the defects per unit. So for the control limit, the lower limit would be 0, and the upper limit here is 7.24. So that's 7.24 here. So this is the upper limit control chart. And then we can compute the number of defects. We already have them for the samples, and we're just gonna plot them here. For example, the 8th sample, the number of defects is 1, so 8 is equal to 1. Or for example, the 16th one is also 1, so 16 is 1. So as you see here, we can plot all of these defects for all the samples on this chart, and then we can test whether this is in control or not. Since none of these data points here, so none of these actually are outside this control limit, all of them are within the lower limit and upper limit. So we say that the process is in control. So it's going to pass our test, and we're going to conclude that the process is in control. So we learned 4 control charts, 2 for variables, the X bar chart and R chart, and 2 for attributes, the P chart and C chart. Is that it? Are control charts enough and sufficient for testing whether a process is in control or not for quality control consideration? But actually not. Even if a process appears to be in control using the control chart, the data may still not really reflect a random process. That means that the variation in the process may not necessarily be natural or random if it passes the control quality chart, because the control charts test for points that are too extreme to be considered as random or natural. Those points that are outside of the control limits, the upper or lower control limits. So what can we do? We need to actually supplement the control charts with what is called a run test. A run test is a test for patterns in a sequence. So a pattern shows that there is any pattern actually shows an unnatural thing going on. That means when a pattern repeated, that means that okay, there is an unnaturalness here because it's a pattern. It repeats it, so something causing this behavior to be a pattern-like behavior. So run tests are done with a sequence of observation with certain characteristics to see and test whether there is a pattern. A pattern can be, for example, an increasing upward trend or a downward trend or a decreasing trend, or it can be, for example, most of your data is below a value, or there is like a concentration around the value. So anything that has a pattern that you can recognize can mean that there is a unnatural thing going on behind the scene. Take a look at this example for the necessity of run tests and the insufficiency of the control charts. So as you see in this chart here, the first chart, there is a trend here actually. So you see that we have used a control chart. This is upper control limit, lower control limit, and all of the data that we have here is actually within these two limits. So the control chart, based on the control chart output, this process is in control. But is it? Let's actually see. So as you see here, this is the data that we have here. So the plot of this data is rising. It has a increasing trend. It's upward trend from left to right is increasing. So this means that okay, there is a pattern here. Something is causing on average the data is rising. So this is not natural. A natural or random event shouldn't have any trend, shouldn't have any pattern. So this is a flag. that cannot be raised by control chart. It would pass the control chart, but there is still, it can be actually observed through a run test. Or the next example, we have a cycle here, as you see here. So the upper and control limit, as you see, all of these examples shown here, the process passes the control chart test, but it has a pattern. So the pattern here is, as you see here, there is a cycle. There is this cycle of going up and down here, repeating after each other. So this is another pattern that shows that there is something going on here. There is a pattern here which makes this process unnatural. The variation in data is not natural, is not random. The next one is the bias. So as you see here, this is the upper control limit, the lower control limit. So based on testing by the control chart, this would pass as a random natural event. But if you look closer, you're going to see that, okay, this is the middle of this control chart, and the majority of data here are below the average majority. So this is an unnatural. There is a concentration of data points around lower limit of around below of mean. This is another pattern here. So this also would not pass the run test here. So run test would actually flag this. And the last one is too much dispersion here. So as you see here, using the control limit, this would actually pass. But based on our observation here, you can see that there are too much scatterness going up, down, up, down, up, down, too much going up and down, too much dispersion of data. So this is another, not easily actually, you might have not noticed it, but too much dispersion, too much up and down, too much fluctuation. It actually flags out as something is going on, raising the flag that there is a cause, an unnatural cause or unnatural randomness here that causes the process to scatter a lot, to disperse a lot. And as we notice here, all of these charts would actually have passed the control charts test. But using the run test and observation, we can see that all of them actually have a problem. There is a pattern here for each of these charts. So these are non-random pattern, and they have to be flagged out as unnatural, non-random processes.